This lesson is the last lesson for this unit on triangles, and in it we're going to cover two of the points of concurrency within a triangle. They're called medians and altitudes, or the segments within the triangle where they're going to meet, and we'll talk about the points of concurrency for those. So the objective is to identify the properties of medians and altitudes of a triangle. So the first definition we have is for a median. A median of a triangle is a segment whose endpoints are a vertex and the midpoint of the opposite side. So in this particular one, we have a vertex and a midpoint of the opposite side. You can tell from the congruence markings. So this segment that connects the vertex and the midpoint of its opposite side is called a median. The concurrency of medians theorems, concurrent just means that it's two or more things that are meeting at the same place. So here we have the medians of a triangle are concurrent, or in other words, they meet at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So in this triangle that they have drawn, triangle DEF, the point of concurrency where all of the midpoints meet in the center is point C. So that is going to be the point of concurrency. So let's look at what this means for this triangle here. Here we have DC is one of the medians. So for DC, that so the median's DJ. To get from the vertex to that center point of concurrency where they all meet, it's going to be 2/3 of the whole length of that median, DJ. Let's look at another one of the medians. Let's look at FH. So the median is FH. So to get from the vertex point F to that point of concurrency C, you've got FC is going to be 2/3 of the entire median, which is FH. And then finally, for the last one, we have from E to G. So from E to G, that's the entire length of the median. So we're going to get from E to C, EC would be 2/3 of the length of that entire median, EG. So that's the formula that we have to work with for medians and the point where they meet. Now that point where they meet has a special name. So let's go down to the next definition. We have several definitions in this lesson. So the next definition, that point of concurrency of the medians, that point where all of the medians meet, is called the centroid of the triangle. And that centroid, it's also called the center of gravity. Of the triangle, because it's the point where the triangular shape is the point where it will balance. So for any triangle, the centroid is always going to be inside the triangle, whether it's an acute triangle, a right triangle, or an obtuse triangle. The centroid where the medians meet is always going to be inside the triangle. The next point of concurrency that we're going to talk about is the point where the altitudes meet. So the altitude of a triangle is the perpendicular segment from a vertex of the triangle to the line containing the opposite side. Now, in this particular instance, the altitude of a triangle, it can be inside the triangle if it's an acute triangle. It can be outside the triangle if it's an obtuse triangle, or it can be one of the sides of the triangle if it's a right triangle. So we'll look at some diagrams that'll help visualize this. Let's go over the next theorem. So the next theorem that we have is the concurrency of altitudes theorem. Remember, concurrency just means that it's two or more things that meet at the same place. So that means that the altitudes of a triangle are concurrent. They are going to meet at a point. So the lines that contain the altitudes of a triangle are concurrent at a point that's called an orthocenter. Of the triangle. So the orthocenter of a triangle, that point of concurrency where they all meet, it can be inside the triangle if it's a acute triangle. It can be on it if it's a right triangle, or it can be outside the triangle if it is an obtuse triangle. Now here's some diagrams below to help you visualize this. In an acute triangle, this point of concurrency where these altitudes meet, the orthocenter is always going to be inside the triangle for an acute triangle. On a right triangle, the altitudes are actually the legs of the right triangle, and then this segment is also an altitude. So where they're meeting down here on the right triangle at the vertex where the right angle is for the right triangle is where the orthocenter is located. And on an obtuse triangle, in an obtuse triangle, you have to extend the sides of the triangle before you can draw an altitude that's perpendicular to it. So that's why this one is meeting outside. Here you have to extend this side to get this altitude drawn, and then this altitude comes through the middle. So this point on the outside of the triangle, the orthocenter, is meeting on the outside of the triangle for an obtuse triangle. Below, I've just listed all of the different points of concurrency for a triangle. We will cover perpendicular bisectors and angle bisectors later. But just to let you know, there are 4 different points of concurrency for a triangle, and we're only going to cover 2 of them, the medians and the altitudes, right now. So let's look at a few problems using this. In problem 1, we're finding the length of a median. So it gives us that SP is 16, and it wants to know the length of SM. So P is the point of concurrency of the medians. It's the centroid. We can tell that from the diagram. So our points of concurrency of the medians theorem tells us that SP, the length of the segment from the vertex to that point of concurrency P, SP is 2/3 of the entire median, which is SM, and that's what we want to know, is the length of SM. So SP, it tells us, is 16, and that's 2/3 of SM. So if we multiply both sides by the reciprocal of 2/3, so multiply both sides by 3/2, so that cancels. We have SM is equal to 2 going to 16 8 times, and 3 times 8 is 24. 24. if you'll just note from looking at the diagram, if the length of the segment SP from the vertex to the centroid is 2/3, if that is 2/3 of the length, then that means that the remaining part of the segment from P to M has to be 1/3. So there's a 2/3, 1/3 relationship. So you should be able to tell there's a 2-to-1 ratio between these two segment lengths. So if you look at this as a 2-to-1 ratio between these two segment lengths, and you can tell that the segment length is 16 from S to P, that means half of 16 is 8. That has this other length has to be 8, and then add those together and you can get 24. You should be able to work these without calculating it, and just by using that 2-to-1 ratio. So let's go down and look at the next problem with altitudes and medians. In problem 2, it just wants you to identify a median and an altitude. So the first one it asks you to identify is AC. So from point A to point C, it wants to know, is that a median, an altitude, or neither one? So a median by definition goes from a vertex to the midpoint of the opposite side. And we can tell from these congruence markings that point C is the midpoint of the opposite side. So that means that AC is a median. So now let's look at the next part of the question, which is AE. AE, is it an altitude or a median? Well, we know it's not a median because it's not going to the midpoint of the opposite side. AC was going to the midpoint of the opposite side. And we can tell here that AE is going down at a right angle to an extension of its opposite side. So if you extend side BD, if you extend it out so that it will meet AE, then AE is an altitude for that triangle. It's just because it's an obtuse triangle is why the altitude is on the outside of the triangle. So let's go move on to problem 3. Problem 3 is definitely a little more challenging problem. It's finding an orthocenter, the coordinates of the orthocenter of this triangle DEF. So in order to find the coordinates of the orthocenter, we have to find the point where two of the altitudes cross. So if we look at this triangle, one of the altitudes that's easiest for us to see is the altitude that's going to go from point E down to, that's going to be perpendicular to the opposite side DF. So that is one of the altitudes of this triangle. And we can see that the equation of this line, since this is a vertical line, every point on this line, x is going to be 5. So that's the equation of the line. X equals 5 is the equation of one of the altitudes of this triangle. Now we need to find another equation of the line of another altitude in this triangle. So let's look at the one that, let's look at the points. Let's look at the coordinates of the points. The coordinates of D is 3, -2. The coordinates of F is 9, -2. And the coordinates of E is 5, 6. So if we could find the coordinates where this altitude, we're going to look at this altitude that goes from point D to side EF. we need to find the equation of that line. Now, I just sketched it there. We need to find the exact equation of that line. So in order to do that, we have to find the slope of EF. So we need to find this, because remember, to write an equation of a line, we need the slope of a line, we need the slope of the line, and we need a point on the line. So we're going to find the slope of EF because the altitude is going to be perpendicular to this side EF. So if we look at the slope, we're going to have 6 minus a negative 2 is 6 plus 2. And then we'll have 5 minus 9. That's just the equation of slope. Difference, change in y over change in x. It's 8 over negative 4. So the slope of that line, the side EF, is negative 2. But we want the slope of that altitude that's perpendicular to it. So the perpendicular slope is going to be the opposite reciprocal, which is 1/2. So now we need to know the equation of the line that contains point D, which is 3 comma negative 2, and it has a slope of 1/2, because that's going to be the equation of this line. That's the altitude that we want. So let's use the point slope form of a line, which is y minus y1 is m times x minus x1. And let's substitute in the point D, which is 3 negative 2. So we have y minus a negative 2 is y plus 2. We want the perpendicular slope, which is 1/2. And then x minus the x value, which is 3, for the point D. So now let's simplify this. We're going to get y plus 2 is 1/2 x minus 3/2. And then we're going to subtract 2 from both sides. So if you subtract 2 from both sides, you're going to get y is 1/2 x. And if we're subtracting 2 from a fraction, we have a minus 3/2. 2 is 4/2. So minus 4/2 is going to be minus 7/2. That's the equation of the line for the other altitude that we just drew. That's the equation of the line from the altitude going from point D perpendicular to the side EF. So now if we take the equation of that line, and we need to know where those two lines are crossing. So to know where those two lines are crossing, those two altitudes are crossing, we have the two equations of the two lines. We're going to take the equation x is equal to 5 and substitute it in for that value of x to find out where these two lines intersect. So here we have y equals 1/2 times 5 minus 7/2. I just substituted in x is equal to 5 for the value of x. So then we have y is equal to 5/2 minus 7/2. So 5/2 minus 7/2 is a negative 2/2, negative 2 over 2, which is a negative 1. So the coordinates of the orthocenter, that point where those two altitudes meet, the x value is 5 and the y value is negative 1. So that's how you calculate the coordinates of an orthocenter.